I want to wrap up this activity that we started before break. We talked about points of concurrency, and we did Discovery 1, and most people were able to do this with no trouble. We sort of did it in class, and then some people did it ahead of time. But we had to find the midpoints. So E is a midpoint of AB, F is a midpoint of BC, and so forth. The way we found these midpoints was to take the corners and plug it into the midpoint formula. So we found each ordered pair that landed in the middle. Then the next job was to draw a segment from that midpoint to the opposite corner. When you do that for all the sides, they all intersect at the same spot. So this spot is called a point of concurrency, and these segments are called concurrent segments. There's a special name for the point of concurrency when you draw all of these, and these are called medians. So all those spots are called medians. When all the medians intersect at a common point, it is called a centroid. So point D is a centroid. Now, the special thing about this is that this point cuts each one of these segments that were drawn into a 1:2 ratio. So whatever this length is, this one would be twice as big as this one. The whole thing would be 3 times as big as the smallest one. And that's true for every median that was drawn. Whatever this is twice as big. Whatever this is twice as big. And then the whole thing is always 3 times the smaller piece. So that is kind of what's special for these. So this spot cuts each median into a 1:2 ratio. Then we did Discovery 2. Discovery 2, we took the slopes of all the sides and we found out what they were, and then we went and wrote the negative reciprocals of them, because to draw altitudes, which is what we're doing here, you need to come from a corner and go to the opposite side, but when it intersects, it needs to intersect at a right angle. So each one of these, every time it hits the side here, it's forming a 90-degree angle. So that makes these lines perpendicular. So altitudes are like a height in a triangle. So you can have 3 different heights here for this triangle. And it's got to intersect the opposite side, coming from a corner and forming a 90-degree angle. Now notice this is where, on the previous slide, this is where E was. E is in a different spot this time, not far from where it was last time, but a slightly different spot. Now, when all of these did intersect this time, these altitudes, they did not hit at a perfect increment. This time it's slightly off from maybe right here where you might be thinking, oh, it was supposed to hit here, but nope, it wasn't. This is where it is supposed to be. So all of these altitudes intersect and come to a common point called an orthocenter. If I wanted to find that intersection, I would want to use any 2 of these green lines, so find the equations of any 2 of those green lines and then solve that system. So one of the easiest ways to solve a system once you know your equations is to type them into Desmos and see where they intersect. So that's what I want to do next. So on the next page we find the slope of, or not slope, but the equation of AF, and we find the equation of EC. Now EC hits AB. So I want to come over here. We found this to be the slope of the line that would hit AB at a perpendicular, as a perpendicular bisector, or not bisector, but as a perpendicular line. So I'm going to use this -2/5. So I'm going to remember that. So I want that, and then I need to see if I could see what the y-intercept is. Okay, if I kept going, I don't think it's going to hit at a really nice spot. So I'm just going to come grab this point right here. So this point is 8, 2. So you either need the y-intercept or you need a point to be able to find a line. So let's look at AF now. So AF, so the slope of, and it hits BC. So the slope of BC was -2. So when we came down here, we found that the negative reciprocal of that would be 1/2. So the slope that we need is the 1/2, and the y-intercept is 0. So that's nice. Okay, so this one will be easier to find because I can just plug it into y equals mx plus b. So this is y equals 1/2 x, and I could put plus 0, but it's not necessary. On this one, not quite as simple. I need to plug it into point slope form. Which is this. Y minus, so I'm going to grab this 2, equals, grab the slope, and go grab the 8. Okay, so I can distribute, and then I would add the 2 to the end. I could also, since I know I'm going to go type it into Desmos, I could skip that distributing, just write it all down like this, and then put the plus 2 on the end. That'll just save me having to deal with this fraction. So, I'm going to write this down real quick. 1/2 x and -2/5 x minus 8 plus 2. And I'm going to go grab a Desmos calculator. Alright, so I'm going to type in the 1/2 x. Oops, I don't want it in the denominator. Notice how I didn't put y equals. If I go y equals, it doesn't change anything. So I can either put the y equals or not. -2/5, and then come out, and then in parentheses x minus 8, and then outside of that plus 2. So here's what I'm wanting, where the intersection is. So right there. So I'm going to write, let's round to the nearest tenth, 5.8, 2.9. You would not want to round those to whole numbers because then that defeats the purpose. We don't want to say 6.3, then it doesn't even look like we've done our job. So you want to go 5.8 and 2.9. Alright, so let's go look at that. So we said 5.8, 2.9. So over almost to the 6 and up almost to the 3. So that looks pretty good. So that is how you would find an exact location. I say exact, we had to round. But that's very, very, very close. Alright, so you may want to make sure you know how to do this for future purposes. Another way to find an altitude, let's say I was not on a piece of grid paper and I just had a triangle drawn. I could use the corner of an index card. So anything that has a corner like that, you want to lay it down and scoot over until you're lined up with the corner, this corner right here. You want to scoot the paper over just enough so that you line it up right on that edge. And then you want you want to be able to see that line. So that's why I have it drawn just so, or placed just so. And then once you have it, you can draw your line, and then when you take it away, it looks like this. This would be an altitude of this triangle, and you want to put a little 90-degree angle in there. So I could do it from this corner, but guess what? This is an obtuse angle. So when I do it from this corner, my line would be outside of the triangle. So sometimes your altitude can be outside the triangle, and I know y'all have seen that when you've done problems, when you have found the area maybe of a triangle. I know you've probably seen when the height is outside like that, and they'll have it with a dotted line, and so there's your height and there's your base. And so if you're finding the area of that, you go 1/2 base times height. So here are some examples of when your points of concurrency can lie outside or right on the triangle. So these are examples of orthocenters. So that means these are altitudes again. So when altitudes are drawn, they make orthocenters. Your orthocenter can lie outside of the triangle. And the time it will do that is if it's an obtuse triangle. So when you see an obtuse angle in your triangle, if all the altitudes were drawn, they would intersect outside the triangle. In a right triangle, our altitudes happen to be the sides, two of the sides that make the right triangle. So that would be an altitude, that would be an altitude. And then if we drew the third altitude, they would all intersect on the corner on that 90-degree angle. So this is an example of when it lies right on the triangle. Then the last thing we did before break was Discovery 3. We took our information from Discovery 1 and Discovery 2. We took the midpoints and we took all of those perpendicular segments that we found, all those slopes that were negative reciprocals. We combined that piece of information and ended up drawing perpendicular bisectors. So perpendicular bisectors are perpendicular to the side that they're coming from, and they're going to come from the midpoint, which means when I draw this segment, it's not going to go through the corner. Okay, so that's sort of different. Now, a perpendicular bisector and an altitude could end up being the same line. It depends on the shape of your triangle. Like if all sides were the same and all angles were the same, then your perpendicular bisectors and altitudes would also be the same. But not here. So every one of these are 90 again, because they're perpendicular. But this time they're coming from the midpoints. Every one of those are midpoints. Okay, so these are going to be called, or this spot is going to be called the circumcenter. So when perpendicular bisectors are drawn, they all meet at something called the circumcenter. This spot, the circumcenter, is equidistant to all the vertices. If I were to draw a segment from here to each vertice, every one of those would be the same length. Now, those would also be, if I drew a triangle where all these corners hit my, not a triangle, but a circle, where all of these corners hit the circle, these would be a radius. So this technically is in the middle of this circle. So that's why it's called a circumcenter. Think about it. Okay, because we have circumferences in circles and things like that. So this is in the center of this circle if I were to draw the circle. Again, this lies somewhere in no man's land, and so we could use our information from the well, you can't use that exact information, but you would need to find the equation of each one of those, at least two of the green lines, and see where they intersect. So circumcenters can also intersect outside or on a circle, on a triangle. If in an obtuse triangle, the circumcenter will land in the exterior. So again, now remember, these are all right here. These spots are in the middle. That would mean that is congruent to that. That's congruent to that. And they're also forming 90-degree angles with the side they're on. So that's what makes them a perpendicular bisector. So this spot is that circumcenter. Okay, so on an obtuse triangle, it's going to lie outside the circle, outside the triangle. In a right triangle, instead of landing right down here like it did on the orthocenter, it's going to land somewhere on the opposite side. So it's a right triangle, that would be called the hypotenuse. Okay, so in a right triangle, the circumcenter will land on the hypotenuse. Okay, so we didn't get to do Discovery 4, and it would have been really hard to do it because we would need to use a compass and bisect all of these angles. We would want to make sure this little angle is congruent to that one. In other words, I'm splitting this big angle into two equal angles. And then I would come through that spot that would split them perfectly in half and just draw a segment. And if I did that all the way around in every single corner, again, I would have a situation where all my points intersect. Now this time, if I draw a circle on the inside, this is called the end center. This end center would land on the inside of this circle. So that's probably why they named it end center. These are all called angle bisectors. The blue lines, the blue dotted lines, are called angle bisectors because I split each angle into two congruent angles, and when you do that all the way around the triangle, they will intersect at something called the end center. And the thing that's special is the end center would be the center of this circle if I were to draw the circle inside my triangle. Alright, so pause the video for a minute. You might want to snap a picture of this because this will be very nice to have later on. This gives you the name of the segments, how to draw those segments, what their point of concurrency is called, so this is vocabulary here, and then what's special about either the circumcenters or possibly the types of segments that we're drawing. Alright, so you are now ready to go work on the concurrency practice. So I would like for you to go pull that up, and I will get with you in just a minute.